Hello folks, welcome back to the Making Links series for Module 10. In this episode we're going to look at how do we increase the rate of reaction. So you can see a little infographic here. This is to just help you remember the 4 key ways that we can increase rate of reaction. So the first thing here is a thermometer. So you can see that the higher the temperature, the faster the rate. That's because when particles have more energy, they collide with more energy. So you're going to have more collisions at or above the activation energy, and you're also going to have just more collisions because everything's going faster. The higher the concentration, the faster the rate. That makes sense because if I've only got a few particles here, then the chances of them bumping into each other is quite slim. But if I've got in the same amount of solution a higher concentration of my reactant particles, then they are going to bump into each other much more often. So I'm going to have more successful collisions when my concentration of reactants is higher. The greater the surface area, the faster the rate. So you can see here, only the outside edges here can be involved in collisions. Whereas here, every single edge and the one at the back and the one at the back here and the one at the bottom, they can all be involved in collisions. Whereas these surfaces here, they cannot be involved in collisions when I've got something lumpy. So of course, the greater the surface area, the faster the rate, and that's because I've just got more exposure of the particles. And then of course, a catalyst lowers the activation energy but is not itself used up, and you can imagine that that's going to increase the rate of reaction because I don't have to put in as much energy for a collision to happen. So I get more collisions here that are at or above the activation energy. So a catalyst lowers the activation energy to make it easier for the particles to react. Okay, let's have a look at a bit more detail. Remember our analogy? What if we made everybody run through the corridors, or we took the time down from 5 minutes to 2.5 minutes to get to class? So this is in the school. If we made everybody run, that would be the same as heating up our particles. So you can see on these particles here, they have less energy. They're moving quite slowly. Therefore, when they collide with each other, they're not going to collide at or above their activation energy, and they are not necessarily going to collide with each other at all because they're not running through the corridors. Whereas here, these particles are moving really quickly. The reason why they're moving quickly is because I've given them lots of energy in the form of heat. They're vibrating more. They're starting to race around the reaction vessel or the beaker. And so when they collide, they're going to have high energy, but they're also going to collide more frequently. So it's always a 2-mark question when you're talking about temperature. Have a look at this question. This is the kind of question that's going to come up. The following equation represents the equilibrium in the contact process. So you can see that 2 sulfur dioxide molecules plus 1 oxygen molecule makes 2 sulfur trioxide molecules, and it's important to note that everything is a gas. Explain the effect on the rate using temperature below 400 degrees. So we're going to underline that because it's below 400 degrees. So it's saying, what if we used a really low temperature, or we dropped the temperature? First of all, it's a 3-mark question. So we know we're going to have to do 3 bullet points. So the first thing that we can say is that the particles will have less energy and will therefore move slower. That's the observation we need to make. Then we need to point out the effect that will have. So there's 2 effects that it will have, as we just talked about before. It's the opposite of what we just talked about, but it's the same process, same concept. Therefore, less frequent collisions and fewer collisions at the correct activation energy. Can you see we've got 1 part here and 2 parts, a second part here. The particles will collide less frequently, but they will also collide with less energy. Therefore, the third part is to say the rate will slow down. But I need both of these points when I'm talking about temperature, always. Let's have a look at the effect of surface area then. This is the equivalent of making everybody physically distant in the corridors or not hang around in packs. So we've got these awesome looking emo kids here all hanging around in a group. And if we split them up, then we get to have anybody is able to have a collision. Even this guy here with the nice, I think it's eyeshadow, or perhaps he's just tired. I don't know. So we've got, it's the equivalent here. If we look, this is like a lump, a great big lump of, say, magnesium ribbon. Let's say I had a piece of magnesium ribbon. You can see that if I zoomed in on the particles, that the particles would be in 3D space. The particles on the inside would be all protected by the particles on the outside. So all of the particles inside wouldn't be able to collide. But if I turned my magnesium into a powder, then the rate of reaction is going to go through the roof because I've split up the particles. And that means that any one of them can have a collision at any time. I've just made it more accessible and more available because now the blue is a powder rather than a pack. These ones here couldn't possibly collide with these ones here, but now these ones can all collide with those ones there. Okay, let's have a look at a question. The experiment was repeated using 1 gram of finely powdered manganese oxide. Don't worry what the experiment was, it doesn't matter. All the other variables are kept the same. What they're saying, the key words here that you're looking out for is finely powdered reactants. So on the axis of the graph, sketch the graph that would be expected, and it's a 2-mark question. Well, here's the graph. So this is the graph that they would have given you. We looked at this graph in a previous video, so it should be familiar to you. They asked us describe the rate at T1, T2 and T3. Now they're not doing that. They're saying, well, what would happen to the rate of reaction if you use powdered? This is a lump here, and this is the powdered line. This is what you would have to draw on the red line. You'll see that the rate here is faster. We know it's faster because the gradient is steeper. And all we'd have to do is draw that we make more volume of oxygen in a shorter amount of time. We've got more oxygen being produced here in a shorter amount of time. But also don't forget that we're not actually going to produce any less oxygen, any more oxygen. The yield will still be the same because we don't have any more reactants. You see, the amount of reactants is exactly the same. The number of blue balls is exactly the same. But, so we can't actually make any more product. The yield is the same always. All we've done is just get there quicker. So explain the shape of this graph, another 2-mark question. Let's see how we go about doing that. We can say that powdered manganese would have a larger surface area. That's what you're getting the mark for there. And increased surface area means that more successful collisions and a faster rate. You need both of those points for the mark. But then the second mark is coming for showing that you know that the amount of product would be produced overall is the same. So same amount of product produced overall. Same here, you're getting 1 mark for showing the faster rate and 1 mark for showing the yield is the same. Here, all you're doing is just putting that into words. So let's have a look at concentration then. If we increase the concentration of a reactant, we've simply just got more of it. So if we've got more molecules, then they're going to collide faster, right? Of course they are. So we're going to get more successful collisions. Simple. Here we haven't got, we've got hardly anybody in the corridors. This would be like having no students or few students rather. And this would be like having like huge classes. And then when the bell went, everybody would be milling through the corridors, and so there'd be a lot more collisions. Statistically speaking, if we have more collisions, we get more successful collisions. Simple. So we'll get faster rate of reaction. So let's have a look at the kind of question. How does the rate of reaction change when smaller pieces of calcium carbonate are used? So this is talking about surface area. Of course, if we use smaller pieces, it's like powdering it up, so the rate is going to increase. Remember, it just says how, it doesn't say explain why the rate of reaction changes. I've put the black in to clarify for you now, but you would get the mark for saying the rate would increase. But of course, we know it increases because there's an increased surface area, so more successful collisions. What about if we decrease the temperature? Well, then, of course, the rate itself would decrease because there's less energy in the particles. So not only will the collisions be less frequent, but they'll also collide with a lower energy. And what about if the concentration of the hydrochloric acid is decreased? Well, obviously, the rate is going to decrease because there's fewer particles, so there's less frequent collisions. One little note here, it's worth saying, if we have a look here, let's draw out a very quick graph, a sketch graph. So if this is my rate of reaction with a low concentration, if I put a high concentration in, then not only is my rate going to be faster, but in this case, I am going to have a higher yield. And the reason why I would have a higher yield is because I have more reactants here. So I can turn more reactants into products. I can make more products, so I've got a higher yield. It's the only one for rates of reaction where you do get a higher yield is when you increase the concentration. So the final way that we can increase rate of reaction is by using a catalyst. And as we looked at before on the MBC website and on the TED video, that's like hiring a dating expert. So here you can see that we always have to put in energy anyway, like rolling a boulder up a hill. We always have to put in energy in order to reach the activation energy. So that is the equivalent of them colliding at or above their activation energy. Then the reaction can proceed and all the hard work is done and we make the products. As you can see in this case, the products have a less energy than the reactants. So we would have a negative delta H, and this would be an exothermic reaction because that extra energy from there to there would be given out as just this bit here. This is what will be given out to the surroundings. But if I lowered the activation energy, so this is what my catalyst is doing, it's making it the products react at a lower energy. So therefore, the frequency of the collisions being at or above their activation energy will increase. So that's all a catalyst does. It just means that there'll be more frequent collisions at or above the activation energy because the activation energy is now lower. It kind of like turns the particles and links them together. So enzymes are biological catalysts. In our bodies, we produce a ton. So lipase, protease, and amylase, we produce them in our bodies. And the thing to remember about the inorganic catalysts or the non-living catalysts, that's the ones that are mostly used in industrial processes. They are transition metals or the oxides of transition metals. So in this case, you've got iron, you've got vanadium-4, you've got platinum. So it's a nice common exam question that's really easy because it's recall. That it says what's the difference, what a transition metal is commonly used for. Well, they're commonly used for catalysts. Let's have a look at the very last question then. It says here, hydrogen can be manufactured by methane, from methane by steam reforming. So in other words, we've got methane here plus a bit of steam or water as a gas. It makes carbon monoxide and hydrogen gas. And that's what we're looking to make the hydrogen gas. The reaction is carried out using a nickel catalyst, again, transition metal, at temperatures between 700 and 1100 degrees C and a pressure of 1 atmosphere. That just 1 atmosphere just means it's 1 times the pressure that you're feeling right now. It's normal room temperature and pressure. So the forward reaction is endothermic, best that we underline that. What is meant by the term catalyst? So this is a really easy 2 marks in the exam because it's recall and it's just a key definition. You always get 2 marks for the definition of a catalyst. The first one is to say that it speeds up the rate of reaction by lowering the activation energy. You usually don't get the mark for only writing speeds up the rate of reaction. You must quantify that by saying it speeds up the reaction by lowering the activation energy. You need to kind of show that you know how that happens. And the second mark always comes for saying it's not used up. So, it's not used up in the reaction. And that's a vital thing about catalysts. It doesn't actually get involved in the chemical reaction itself. So that's it. Hopefully you found that useful. See you next time. Bye.